So, I will sort of be continuing on the theme of the last talk, but hopefully there won't be too much repetition. Well, I will be presenting an epistemological theory based on empirical data, the kind of data that Mario was also talking about. So let's start with some wishes what we should have for an epistemological theory. And you can then compare it as my theory goes along, how it fulfills them. We will return to this in the end. So I think an epistemological theory should not require any unreasonable ontological assumptions. Well, this is very vague, but it will become clear in the end what I mean by this and how my theory fares in this regard. I think in modern philosophy, an epistemological theory should be part of a generally empiricist philosophy. It should be able to explain the apparent objectivity of at least some mathematical truths. I'm saying apparent objectivity, maybe it's not objective, but some mathematical truths certainly appear to be objective. It should not make applications of mathematical theories in empirical sciences a miracle. And this is important. It should not read mathematics of its special character. Mathematicians have certain ways of working, and if our epistemological theory doesn't fit with those characteristics of mathematics, then something's clearly wrong. And finally, I think everybody agrees about these. But this is the one I want to introduce in this talk. With the best scientific data we currently have about mathematical cognition, it should not conflict with philosophical theories. Okay, let's start. I'm going through some empirical data very much in the same style as Mario, so I will be skipping through some of these. You already heard a lot. But there's, sorry for the long quote, but it's a nice one from a neuroscientist, Anders Nieder. It's currently thought that basic numerical competence does not depend on language. It's rooted in biological primitives. It can be found in non-human animals, also in infants. But it deals with a numerical estimation system. So this is the starting point. Let's think about that a bit. I think it's convincingly established that many non-human animals have a basic ability to recognize numerosities. They don't focus on duration, they don't focus on size or other magnitudes. These experiments have been controlled for many variables, and it seems clear that these animals are processing observations based on the quantity of the objects. This is hardly surprising when we consider animals like primates, like chimpanzees, for example, but this has also been detected in rats and even goldfish, very small animals which you wouldn't normally associate with any sort of numerosity sense. Rats, for example, they can distinguish the quantity of tones from the duration of them. And the goldfish, based on the number of objects drawn above a hole, they can choose the right hole to go through in order to get food. Also when we control it for the surface area and illumination of the objects. An experiment showed that human infants have a similar ability. The most famous experiment is the Karen Wynne experiment in her paper in Nature, when it was shown that babies react to the so-called unnatural arithmetic of 1 + 1 = 1. So the baby sees two dolls put behind the screen, but the baby doesn't see that one of the dolls is taken away secretly. And when the screen is removed, there's only one doll. And the babies are surprised by this, which we know because they look at the setting for a longer time. This is a standard methodology in these kind of experiments. And this has been varied for all kinds of variables, and it seems clear that not only do they observe or categorize the observation in terms of numerosities, but also the changing quantity is more important than variations in size, shape, and location of the dolls. So you can change a Mickey Mouse doll to a Donald Duck doll. That's not surprising. But it's surprising if there's only one doll when they expect two. But these experiments and dozens of others, I think they show conclusively enough that many non-human animals and human infants have some kind of ability to distinguish numerosities, and it plays a central role in how they process observations. I don't want to contest this anymore. If anybody is not familiar with this stuff at all, I recommend Dehaen's number sense and Dehaen and Brannon's collection of articles about the empirical data. But people get too excited about this, because we should be very clear about what the empirical data really tells us. For example, Wynn's paper in Nature was called Infant Arithmetic. And is it any surprise that mathematicians and philosophers were skeptical of these ideas when we are saying that infants are doing arithmetic in this experiment? I think that as a guideline we should prefer explanations which postulate fewer and less developed abilities. For example, in Wynn's experiment, it is clear that they process observations in terms of quantity, but why would we say that they are doing arithmetic instead of saying that they are keeping one numerosity in mind? They are not doing addition or subtraction. At least that's not necessary. We don't need this mode of explanation. And I think this danger of postulating unnecessarily developed abilities is already present in terminology. So I will be talking about numerosities when I refer to these non-linguistic concepts that animals and infants use to process quantities. I will also use the word numerosity for the less developed verbal representations of quantities. Because as a philosopher, I must respect that natural number has a specific meaning as an object of BA or Samsa's formal theory. Natural numbers form the omega sequence, and we should not confuse the more primitive forms of dealing with numerosities with this. And when I talk about arithmetic, I'm talking about a sufficiently developed language-based theory of numerosities and operations on them. When I'm talking about these non-linguistic ways of processing numerosities, I'm talking about proto-arithmetic. And finally, when we are talking about arithmetical systems of natural numbers, in the standard sense in philosophy and in mathematics, it's best to talk about formal arithmetic or something like this. So these are important distinctions in terminology I think we should make. So how about the philosophical relevance? This proto-arithmetical ability, which I'm sure exists, what philosophical relevance can it have? Well, one prominent theory is conventionalism. Not so prominent anymore maybe, but used to be prominent in the last century, at least in the latter half of it. But if our arithmetical ability is based on proto-arithmetical ability, which we share with rats and fish, it would be very strange to say that mathematics is only about conventions. Or are we claiming that we share conventions with goldfish? But anyway, I think the empirical data is strong enough that it should enter the philosophical discussion. That's my point. I don't want to make any conclusions yet. But what is the proto-arithmetical ability? Sorry, what?
What's the claim?
The claim here. The last one. Okay. Yeah. So, what is the proto-arithmetical ability? Well, it starts with what cognitive scientists call the approximate number system. It's an estimation system, and it consists of two main parts. First is the ability to subitize. This is what Mario demonstrated to us. In our field of vision, we can determine the cardinality of objects without counting when the numerosity is small enough. And second is the so-called analog magnitude system, which is a way of keeping track of quantities in the working memory. It should be made clear by now that this should not be confused with arithmetical thinking, because it quickly loses accuracy with more than 4 objects, and it can only be properly characterized as discrete when it comes to small quantities. With larger quantities, it becomes increasingly analog. So, from this proto-arithmetical ability, how does arithmetical thinking develop? Well, already in the term proto-arithmetic, there is this sense that arithmetic develops upon it. And this is indeed how cognitive scientists see it. And the common explanation is that ANS is the basis on which arithmetical develops with the help of sufficient linguistic ability. But this is still to a large extent a conjecture. It's not empirically verified. Like Markus talk, for example, pointed out several difficulties in how we even get the natural number sequence out of these origins. And philosophically, this conjecture is absolutely crucial. I propose this argument against conventionalism. Well, if the two systems are independent of each other, obviously the argument would crumble right away. So the important matter is not that the ANS exists or that we can describe it as proto-arithmetical ability. The important matter is whether arithmetical thinking actually develops based on the approximate number system. The question is, can we track a continuous development from the ANS to develop arithmetical thinking? And there are problems with this. One important problem is that the ANS does not disappear. Like you just subitize these small quantities of dots. It doesn't disappear. Adult human beings use subitizing, they use the analog estimation system, and their ability closely resembles the primitive ability of non-human animals and infants. So in adult human subjects, there are two systems for dealing with numerosities. There is the approximate estimation tool, and there is the language-dependent system. But of course, this in turn does not suggest that the developed way of thinking about arithmetic did not develop out of ANS. There are many cases, for example, optical illusions. We know that we have better knowledge, but we still see things in this primitive way, which confuses us in optical illusions, for example. Fortunately, these questions have been studied empirically. And the important point for philosophy is that brain is full of different types of neural filters, which separate important content in observations from the irrelevant content. This is why it's so difficult to have visual recognitions in robots, for example, because robots don't come with these sort of filters. And crucial to the matter at hand, part of this automatic brain activity has to do with quantities. Quite a lot is known about this ability. As we saw in Mario's presentation, it is sort of quasi-logarithmical. It's easy to tell the difference between small numerosities. We can tell the difference between 10 and 20, but for example 19 and 20, it's impossible to recognize the difference without counting. But here's an interesting point. This is mirrored in what happens in the brain, because not only are there distinct areas in the brain for numerosities, but there are also number-specific groups of neurons. So when a monkey is presented with two objects, a specific group of neurons activate, independent of the sensory modality, whether it sees or hears or it's being touched 2 times. And when there are 3 objects, a different group of neurons activates. But there's always some noise in this. It's not only these neurons. So a little part of the neurons for 2 activate when the monkey sees 3 things. And as the numerosities become larger, the noise becomes larger. And the same phenomenon has been detected in human beings. So the nature of the approximate number system is mirrored by what happens in the brain. Well, that is not all, because some primates have the ability to understand symbols assigned to concepts like numerosities. And the same number neurons, so-called number neurons, activate in the monkey brain when it sees the number symbol 2. And when we simulate a non-verbal account of counting to monkeys, there is a difference in the brain area that activates compared to when the monkey sees the group of objects at once. But a large part of the activated neurons are the same as with the approximate number system. So when the monkey is counting, it was dealing in large part with the same representations from numerosities as it subitized. So what does all this suggest our ability, the numerosities, to be? I think the best hypothesis that our basic experience about small quantities are given by the approximate number system. And as we develop the linguistic ability to count, we no longer require the ANS for a numerical ability. We never lose this, but slowly the primitive ability is complemented and in part replaced by the language-based one. Well, obviously all this needs further study. It's not conclusively established yet. But the data clearly points to the direction that our verbal ability with numbers is built to accommodate the primitive non-verbal system. And this is hardly surprising. The brain works this way. There are some existing connections which deal with quantities. When we get new information, the brain uses the existing connections. But this has important philosophical implications. I think strict forms of conventionalism are in trouble when we talk about arithmetical knowledge based on this data. But let's move to epistemology a bit more. I think there is a relevant difference here to be made between linguistic concepts and primitive concepts when we think about the ability. So whatever capacity the goldfish uses in distinguishing between small numbers, it's not the same one as mathematicians use in proving theorems. But if we accept the ANS-based theory, arithmetic is not only about conventions, so it's not only about linguistic concepts. And the question is, what else is it about? One natural suggestion is that it's about objects, and Birch, for example, has used subitizing to this effect, that there are objects for subitizing for numerosities, and these objects are natural numbers, so there's this sort of direct connection to natural numbers. But as our guideline is to use as weak explanations as possible, I think this is not warranted, because we can deal with comparative concepts like fewer and more and have the same sort of knowledge of the small numerosities. And these comparative concepts can start to form into actual numerosity concepts in the brain, leading to there being specific groups of neurons representing each small numerosity. And nowhere do we need natural numbers as objects. But this does not mean that arithmetical knowledge could not be objective, because obviously there is this difference attributed to Price normally between objective truth value and the existence of mathematical objects. And it's a quite common position to believe that statements like 2 plus 1 is equals 3 is true without there existing such things as numbers. And normally we refer to conventions and structures or such explanations for this. But here I suggest that 2 plus 1 equals 3 is true because it corresponds to something in how our brains are hardwired to process numerosities. So is this enough to make arithmetical statements objectively true? Well, this requires further analysis. Objectivity is a very complicated philosophical issue, but to me it seems clear that some sort of objectivity is involved if we share this brain structure with rats and goldfish. It doesn't make sense to say that this is not an objective, this knowledge is not objective in any way. Maybe this is too weak for Platonists, but I think it's the relevant sense of objectivity in this context. Well, I think I need to skip this. How am I doing time?
You still have like 15 minutes almost?
Sorry, 15?
Yeah.
Okay, so I will move to this.
I mean, a bit less.
Okay.
12.
Okay. So, Mario already was talking about this. There's a very important, what happens when we develop arithmetical ability beyond that of the approximate number system? Well, if we start from the hypothesis that the children have some grasp of the general idea of a successor, I think we're on the right track. And we need language and the tools that language can give us to generalize on this idea. I don't mean a formal understanding of successor function or anything like that, just a general idea of one numerosity following the other. But at this point, we must be really careful about confusing our knowledge of developed arithmetic with the psychological processes in developing it. For example, the Carey paper, I think she makes a mistake there. She talks about these logical and ontogenetic programs of accounting for the origin of arithmetic. And she holds that we can use our knowledge of the logical program, which means our knowledge of axiomatic systems, for example, to characterize what is known about numerosities in the ontogenetic program, about the origins of numerosity concepts. So in this concept, we could use Dedekind-Bound axiom to characterize the ANS. But this is something we should avoid as far as possible, since the key question in the whole matter is whether there is a continuous development from the ANS to axiomatic arithmetic, and what kind of development this is. We cannot just take these developed results and explain the development. So in this way, we don't get such strong assumptions, and we cannot explain arithmetical knowledge in so seemingly such convincing ways as Carey, for example, does. But I think there still exists strong data that we can use to characterize arithmetical knowledge. I think because the tradition, there's, let's face it, very little empirical data that is relevant to epistemology of arithmetic. We should be all more interested in this. And it's not just a philosophical exercise, because obviously the nature of arithmetical knowledge under the current understanding is empirically underdetermined. So we need philosophical explanations to make sense of what's going on in there. And here we come to my theory. I claim that arithmetical knowledge is contextual a priori in character. Well, if the ANS-based theory is correct, what kind of knowledge do we get? I propose that we don't need to use the dichotomy between a priori and a posteriori, but not in a Quinean manner. I don't reject this dichotomy. Rather, I think that it doesn't exhaust the possibilities. Well, why not? Well, I'll move to the Latin pronunciation. Why not a priori? So let's consider the statement 2 plus 1 equals 3. It sure has the appearance of being a priori knowledge, because we just use successor function to the first number 3 times in both cases. And thus understood, there is a clear sense in which arithmetical knowledge appears to be a priori. But it's not so simple when we look at this current wider context, because axiomatization was a very late development in the history of arithmetic. In the modern context, it's easy to see arithmetic as a priori knowledge, and I will argue that indeed in this context it's best described as such. But the context did not come out of nowhere. Earlier I distinguished between conceptual knowledge in a primitive sense and a linguistic sense. If arithmetical knowledge was only about the latter, it could be understood as strictly a priori. But it is not. It is also about the proto-arithmetical numerosity concepts given to us by the ANS. In the development of arithmetical knowledge, an important part is our experience using the ANS, what comes to us as empirical facts. So when we first accept the arithmetical statement, I'm talking about the children now beyond their infant years. When we accept an arithmetical statement, we do so because it fits with years of experience, maybe not years, but at least many, many months of experience in processing observations in terms of numerosities. It doesn't come out of nowhere. It's not just something that we learn by rote memory. Well, obviously, a priori knowledge should not be required to be totally independent of empirical aspects. Let's avoid that confusion. In the trivial sense, we of course need to hear or see in order to understand what words mean. I'm not talking about anything like this. What I'm talking about is that arithmetical knowledge is empirically constrained in a stronger way than, for example, a statement like all bachelors are unmarried is constrained empirically. We have proto-arithmetical knowledge long before we have developed the necessary linguistic ability to characterize it arithmetically. This is not the case with statements like all bachelors are unmarried. But I am talking about arithmetic clearly in a wider way than just axiomatic systems like PA. I think any ANS-based system dealing with numerosities which has an explicit number of words or symbols and rules is arithmetical insofar as it conforms to the intuitions given to us by the ANS. And with this wider understanding of arithmetic, are we now in danger of losing the objectivity of arithmetical knowledge? This is something I claimed earlier. There are, for example, these tribes that have numerosity words for 1, 2, and many. And in their so-called arithmetic, 2 added to 1 is many, but so is 2 added to 2. And they work also based on the approximate number system. And what is going on in here? Well, we can dismiss these tribes as unarithmetical, but for example, Mayans had really sophisticated systems for dealing with numerosities. They could calculate them up to billions. But they did not have arithmetic in the sense that we have, in the sense of proving theorems about all numbers and all this, involving infinity and these sophisticated concepts. So in one sense, Mayan arithmetic was very much like ours, but in another, it was essentially different. And in modern mathematics, obviously, there are approaches like ultrafinitism, which are essentially different in characteristics from PA. So if arithmetical knowledge is objective, which arithmetic are we talking about? I think we should take developmental aspects seriously in philosophy when we talk about this question. I think there is a crucial step from non-arithmetic to arithmetic, but it's not the one when we move to axiomatic systems. It's the one when we move from proto-arithmetic of the ANS to the language-based arithmetic. So this way I count any sufficiently developed system which has words or number symbols and rules as arithmetical. But can arithmetical knowledge still be characterized as objective? Well, I have very little time, but I want to go through this quickly. In a debate concerning moral realism, these kinds of explanations have been considered to be a bad fit with moral realism, because this is an evolutionary explanation. We have evolved to use this number concepts. How do we know that these number concepts respond to something in reality? For example, Clark Doan has argued that it could be that 1 plus 1 equals 0 is the case in the mathematical universe, realistically construed, whatever that may be. But the evolutionary advantageous one would be 1 plus 1 equals 2. Well, that example might be far-fetched, but it is a good question to ask which ANS-based statements are objectively true, if any are. Well, I don't think the analogy between moral values and arithmetic is perfectly apt. But even so, this kind of argument is targeted against Platonist approaches, when we assume that there is something more to arithmetical knowledge than this evolutionary, than these abilities based on brain structure which have been given to us by evolution. Because there is no evolutionary gap if you consider the objective arithmetical truths to be the ones based on evolution, the ones based on our brain structure. And I hope to have shown already that the objectivity of ANS is strong enough to make the possible counterexample of 1 plus 1 equals 0 without sense. Obviously, there are cultural, conventional factors involved. So what I'm saying is that arithmetical knowledge is never completely conventional. This is the important point. And there is no epistemological gap involved in this. So in this sense, arithmetical knowledge can be characterized as a priori, but only in the context set by empirical facts. This is the important point of my theory. So we all know the arguments against Kitcher. I will be skipping these. But there is a good argument, counter-argument to my position. Why are we talking about contextual a priori? Why are we not talking about empiricist mathematics. Because if we, even if we only can perceive small numerosities based on ANS, obviously we experience pluralities of objects much greater than that. So cannot we say that we experience the world in arithmetically in this larger way? We experience larger numerosities than the ANS. But evidence suggests otherwise. Because there is the roughly logarithmical nature of ANS, it suggests to me at least that we don't observe large pluralities in the same way as small numerosities. And this is also mirrored in what happens in the brain. When we perceive that small numerosities, different brain areas are activated compared to one with large numerosities. Well, there is an example of that, but I will have to skip it. So this is the final part. I think we have to combine empirical aspects and a priori and get the contextual a priori. And this is something which resembles approaches by Putnam and Kuhn, who also have contextual a priori notions. So in Putnam's notion, there are statements in science which can only be overthrown by new theory, sometimes by revolution in new theory, and not by observation alone. Such statements have a sort of a priority prior to the invention of the new theory, which challenges or replaces them. They are contextual a priori. And his example is Euclidean geometry. It's a false theory about the world, but it can be contextual a priori. This is not what I'm after. I don't want to say that a theory which has false beliefs can be considered to be knowledge. I define contextual a priori knowledge to mean a priori in a context set by empirical facts. And I don't mean this in these sort of trivial ways that we can study these facts empirically. What I mean is that we learn the basic rules concerning numerosities empirically by observation. But this can only happen because of the ANS. So when we see 2 apples and 1 apple grouped together, we see 3 apples. We could see a lot of things, but experiments show that numerosities are central to the way our brain processes such observations. So when we learn this, we have done this countless of times. That is why yesterday there was this difficulty. How do we know that we refer to the same object when we talk about the number 3? This is how we know. Because we have the brain structural basis for numerosities. I think I'm out of time. So this is my last point. This way, when I characterize arithmetical knowledge as contextual a priori, it's not just another Kuhnian paradigm, for example, because it's an effectively inevitable way of experiencing the world. So if something is so tightly connected to empirical aspects, yet we use a priori methods in the study of this subject, I think our arithmetical knowledge can be both objective and contextually a priori in character. And I have to end here.
Thank you. Okay, we have 4 questions. Andrea, Luca, Mario, and Gabriele.
Thanks for the talk. I think it's a very interesting picture to get together the cognitive and the more developed and more philosophical issues, which are usually kept very severe. And now I think I have a lot of problems when you put them together. And what you're saying is that you can see the a priori aspect of our computation of arithmetic, but we have to tie it to some contextually determined empirical facts. Now you of course say that the ANS give us an effectively inevitable way of experiencing our work, but it is our work. So when you start talking about a priori and a part of conventionalism and a part and semantic issues, then the question is, are arithmetical sentences necessary or not? And so the issue is here, if you add another word, or if there is another word with cognitive capacities different from ours and the ANS different from ours, would the same sentences be true, or we would have a different mathematical theory?
That's a very good question, and obviously we have to deal with some really heavy philosophy there about possible worlds and all this if you want to take that approach. But yes, it's sort of been a conscious decision not to go into those matters because then the focus would be on that. So I sort of want to take this constructivist approach in this sense, that without human beings or without these non-human animals which have this ability, it doesn't make sense to talk about arithmetic. There wouldn't be a subject matter we understand or we can talk about. So basically that's my approach here, but that is not my approach generally in philosophy. So I have to leave this question unanswered because it goes too far into that territory.
Okay, we have a lot of questions, so these short questions and fast solution answers.
Yes. First, about the objectivity, the fact that it reminds me of something that Kant said about objectivity in a different context, but it's very similar. If you say that something is wired in the brain in some very basic and at some very basic level, and something is based on that's the best way to make it impossible to have objectivity. Kant said this is what the skeptic most wants, because I can say I am done in such a way that I think like this, and we can't say it is 2 plus 2 is 4 objective. This is the first point. Second point is the fact that what puzzles me, it is in the spirit of what Markus Pantsar said before. What puzzles me is the fact that even when you are a mathematician, you have a full-fledged knowledge of numbers, say, but there are people who have the same cognitive limits in dealing with, for instance, very long symbolic computations, etc. The analogous limits, only on a different level, but analogous limits. Mine is like the one of the goldfish. For Neumann's is very different in doing very, very long symbolic manipulations. So the point is, what has all this to do with possessing the concept of number? I still don't understand because even when you have full-fledged capacities, abilities, there is the same problem. Simply we can't deal with too large numerals, etc. So why here it is? What is the relevance in the concept of number?
Well, the first question. As I mentioned, objectivity is again one of these problems that I cannot go full on into this in such a short presentation. But we might not want to call this kind of knowledge objective. We might want to have another term. I'm not a fan of terms like intersubjectivity, but I would say this is maximally intersubjective. And the point is that I define objectivity here as an opposite for these conventionalist approaches. So that is it. And for the second, I think my point would be that if we have a full picture of how our number concepts developed based on ANS, and if indeed this is correct, this is what happened, our philosophical problems like that would be illuminated. I don't see there is, it's not just this context of discovery, but we also understand better what is going on with concepts like natural number, because obviously there is abstraction going on already in here, because these are independent of the modality, the numerosity concepts with the goldfish, for example. So there is some sort of abstraction going there, but then we just go further and further in our abstraction. And how this happens, I cannot tell because it's not known, but I think we should start building a picture from the very beginnings and not take this mathematical concept of number independently of all this. I guess that's the best I can answer now.
Please short.
There were a lot of
Please
things.
short, because Luca's question was not exactly short.
Okay. I have two remarks, very short. The first one, many of the things that you were mentioning concerning IMS, I think that can be put in question as really concerned with something as graph of quantity. For example, Carey-Winn experiment. It's true that we can describe what the babies do using the notion of quantity, but there is no evidence that we are doing that is exactly reacting to quantity. Could be, you could imagine as a sort of cerebral systems in which there is only retention that is there. There is a difference between that and that, retain that, and you are surprised when you see that. There is nothing to do with quantity.
But then again, there's this problem that quantity performs other way than other such differences, like in size and all this. So there is some difference there. But yes.
Okay. So there's another question, a suggestion. I think that in order to see the possible connection to INS and mature arithmetics, I suggest you to look to Piaget's works. Piaget answers are totally. But the questions that Piaget was putting are very, very much interesting in trying to see what sort of competence we have to develop in order to grasp something more than INS.
Yeah, that's a good suggestion. You made that a couple of years ago already, and I have heeded your advice.
Mario.
This is a very short question. What is the, linked to what Andres, what is the inevitability doing for you exactly? What you have written inevitable in italics, and I want to know what theoretical work, what conclusions are you drawing from this apparent inevitability?
Okay, so this is when I want to distinguish it from a Kuhnian notion of contextual a priori, that this is just some theory that we use, because it's a theory that we cannot escape. So that's
so this cuts through any developments. I mean, the ANS still forces us to see the world and experience it as we do.
yes, in some ways.
Now,
Yes.
what does it prove? What epistemological question does it clarify? Because it's inevitable for me to fall into the Müller-Lyer illusion, even though I know explicitly and consciously that the two lines in the Müller-Lyer are the same length. I can't help but see them one shorter than the other, right? So it might be that we are in a similar case. I mean, I'm just trying to play the devil's advocate. Yeah, that's what I'm talking about. So no matter how long you stare at this picture, you see one shorter than the other, and you're entirely wrong. And so I just want to press you on that. So the fact that something is cognitively speaking inevitable might not carry much epistemological weight unless you say something more.
Okay. Well, yeah. I hope that I actually have said something more. That it's also inevitable that we start to develop our language-based arithmetical understanding based on the ANS. So we accommodate our new understanding of numbers, language-based ones, with the primitive system. So this is what I know that it doesn't carry the kind of epistemological weight that you're talking about, but I still think that there is a relevant difference there, because it is not like situation like that, because you know that you're wrong with your impression. With the ANS, it's not like that. We are not wrong when we subitized your examples, for example. We were not wrong. We were just using a more primitive ability there.
I don't want to carry this too long, but there's a similar illusion which we are trained that has to do with numerical perception. It's the Ginzburg examples, and there you're systematically wrong. You judge one collection to be larger than the other, whereas it isn't. It has the same number of items.
Yeah.
It's just because of their position.
Yeah, there are many ways of sort of screwing the brain with, for example, number symbols and collections confuse the brain already, so you cannot subsidize anything reliably. But I think these are pathological cases. They are important in a sense, but more important is that how successful the ANS is most of the time.
All right, good. Yeah,
Sorry, don't need.
And I've got to get up, otherwise I'm not able to say anything on the law. Now, I was wondering whether a better way of explaining the relationship between ANS and proper arithmetic and whatever it is might be the relationship that there is between, say, common sense and science. This is a difference that you find all the time in all manners of ways. There is some knowledge that we accumulate by means of common sense about, I don't know, people's character, or before all sorts of ideas which allow us to navigate in personal relationships, for example, which when seen from a scientific, psychological point of view, are shown to be full of mistakes, full of mythology built up by people. So I was wondering whether something similar is happening here, namely whether we should talk about the relationship existing between ANS and arithmetic proper is precisely this. No, ANS is the type of arithmetic, one-to-many, or whatever it is that people do culturally when they have to go, when they have to navigate, when they have to solve that type of arithmetical questions which are put before them by their environment, by the way that they organize themselves. But as soon as the problems, the magnitude of problems, or the difficulty of problems grows beyond what the immediate environment actually presented them with, of course they have got to get into science, into justifying, first of all, their ideas about numbers and about counting and so on and so forth. And then getting into, let us say, arithmetic problem. So, in a sense, and then I finish with this, arithmetic perhaps ought to be thought not just as one theory based on particular type of number senses or whatever it is, but as a sequence of theories, in a sense, like in empirical sciences. So we start from what we need in order to cope with our environment and form our arithmetical law, if you like. But then this has to be overcome because of course there are lots and lots of other problems which are put before us, which we cannot solve with that common sensible view, and therefore we are asked to provide justification for things when our calculations don't work.
Yeah, I love that approach. Certainly.
Since I'm afraid we cannot settle today what arithmetic is, I'm afraid that we are running very late, and so we have to go to the next speaker. If you want to comment, if the next speaker can comment, so that please.
Okay,
Go
so
ahead.
I'll give a really short answer. So I'm very sympathetic to the idea that there are many different arithmetical systems and also many levels of that. So I have no objection to that. I think that's a very good approach to take.